So we just did a brief online survey, and we knew that in the audience, well, we have all kinds of people. Some know nothing about AI, some know quite a lot about AI. So I'm glad to see so many people here interested in AI. But before we go on, let's hold on for a second. When you hear the word AI, what came to your mind the first? What's your first impression? For myself, as recent as a few years ago, when I thought about AI, I always have these robots, professors, hiding somewhere in a lab, making a robot, hoping that it won't destroy humankind. That's the kind of impression I got. And I can tell you that this kind of impression is really blocking me from going deeper, because for me, unlike all these speakers here today, I don't get a PhD degree. I'm not a professor. I've never built a robot in my life. So for me, AI is something that's so remote from me. I love AI, I like talking about them, I like to discuss with my friend about how our world will be with the AI technologies, but I never ever thought I can learn it myself. And that is the thing, one of the my job today is to break that conception, and I don't think that's correct. So, in order to prove that AI is beyond just robot, let's do a small test. I'm going to play some music here. It's not long, 30 to 60 seconds. And while you enjoy the music, I will let you know later what this is for. Hopefully we'll play. Okay, we'll stop here. And now, I'm going to play another music, also around 30 to 60 seconds. All right, let's stop here. If I tell you that between the two music, one is written by the famous musician, Bach, and another one is written by an AI program that listened to a lot of similar style music and created its own. So let me ask you guys, how many of you think music number one is a fake one, is written by AI? Can you raise your hand? The first one? Okay. How many think the second one is fake? It's written by AI. All right. All the people who raised hands the second time, they are wrong. Well, the guys who created this music, actually, they invited 1,000 people to go through this test. 25% of those 1,000 people are professional musicians, and they couldn't tell the difference. So don't feel embarrassed if you did it wrong. The point here is that AI is right now in a lot of fields, well beyond the sci-fi movies. It's in artistic, and later, I believe it's Said, will show us some visual arts that's also amazing. Now, we talk about AI is well beyond robots. And I also talk about, well, in the beginning, I thought AI is something that's so remote, it's not something that I can touch. But it turns out that I'm wrong, and I'm going to show you today the very fundamental thing about AI. Hopefully, after this section, when you walk out of this door, you will no longer feel that AI is something that you cannot touch. You should be able to learn it yourself, regardless of what your background is. Before we move on, let's clear up some concepts first. When we talk about AI, like we hear the news, we are mixing all these terms together. Machine learning, artificial intelligence, deep learning, neural network, they are all, they all sound the same, but they are actually different. Artificial intelligence is something that's a very broad term. It's very generic. Anything that wants to achieve a goal with interaction with the environment, you call that AI. It's a very broad term. It doesn't refer to any specific technologies. Well, machine learning is a particular way of implementing AI. This is something very interesting because a lot of you guys are from IT industry. You should know that when we write a program, you tell the machine what to do. For example, when my son built his robot, in his program you will say, step forward 10 steps, turn right 90 degrees, step another 5 steps, turn left. If there's a wall in front of me, turn right again, so on and so forth. So it's all the steps are written in the program. If you don't give the steps, it doesn't know what to do. Machine learning doesn't work that way because, does it work? Do you think it will work? Oh, it's not connected. Okay. Sorry, thank you. It is Bluetooth. All right, so machine learning is something that's, it's not something new. It was created in 1970s. It was actually first came out in 1969. With machine learning, machine can actually do more than just what you tell it to do. That's all it is about. Machine can learn. And then deep learning came along. With deep learning, well, again, it's not something new. It was created in the 1980s. Deep learning is a special kind of machine learning, and our talk today will focus mainly on deep learning. And that is something that's creating all this buzz today. So that you might want to ask, why today? It was created in the 70s and 80s. So all these old technologies, there's nothing new. Why are they all of a sudden becoming popular today? The answer is, while it was created, remember it was in early 80s. At that time, we have very little computing power. But AI really need a lot of computing in order for it to work. Yeah. So why is it becoming popular now? It's because, first of all, today we have cloud computing, we have a lot of computing power. And second is, before internet, we barely have any data. Now we have a lot of data, and machine learning is a data monster. It needs to eat in a lot of data in order to produce a result. And the third, well, we have better model. Now let's get into deep learning, how it works. And that's what I'm trying to do today, to tell you what's the fundamental building block of deep learning, with something also called deep neural net. Well, it's called neural for a reason. It's inspired by human brain, how human brain works. What you can see here is a neuron, that's a brain cell in your brain. You can see a lot of these blue dots. That's the information coming into this brain cell. So after the information comes in, this neuron will process the information, and depending on what kind of information it gets, it sometimes releases these red dots. and pass that to the next neuron. As you can see here, the red dot sometimes is released, sometimes it's not. That depends on what information comes in. For example, if your hand touches something really hot, that signal gets released and your hand comes back. In order to simulate this, we come up with some mathematical model, and it's actually very, very easy. Okay, so you see here, there's a neuron, and there are 4 pieces of information that comes in. Because it's computer, all those information that comes in are numbers. And there are so many information come in, 1, 2, 3, 4. How do we know how to deal with them? One way to deal with them is give them some weight. It's like when you ask your friends, what kind of car I will buy next, you will listen to some friends more than some others. So in this case, we just say, I'm going to weigh them, each input, sum them up together, that's my output. As easy as that. If we give it a concrete example, well, let's say we trust the second input more, we give it 40% weight, and we add them up together, we come up with the end result. So as easy as that. However, there's something it's missing here. Well, yes, we get the result 72, right? But how is it related to this red dot that's being released? There's something that's missing here, which is called a division. So we get a number here, 72, great. But what does it mean? We want it to trigger the release of the red dot, right? If we zoom in to our real neuron, that's how it looks like. So you will see here, this is called synapse, and this is called receptor, biological terms. And you can see here between the 2 neurons, there's a gap in between. And the information from this neuron doesn't pass through because of this gap. And you have something called neurotransmitter here. Those guys are responsible for passing the information through. And when those neurotransmitters get released, information passes through. So similarly, we will create something to simulate this process with some math formula. There are many activation formulas, and this is just one of them. As you can see here, with this math formula, the X is the signal that's coming into the neuron. As what we showed earlier, that was a 72. And you compute this formula in output somewhere between 0 and 1. 1 means it's turned on. You pass information to the next neuron. If it's 0, well, it doesn't pass information through. That's the activation network. So if we put them all together, right now you can see this whole thing is a neuron that has 4 W values. We call them parameters. And we have this output that's a sum, weighted sum of all these inputs. And we add them, add in the activation function. And that is what the neuron is. Pretty simple math. I think it's like elementary school math. Now, with all this together, now we know what a neuron is. We stack many, many neurons up together, it becomes a neural network. As you can see here, each of these neurons is connected to each of the neurons in the prior layer. It does the weighted sum, it does the activation, and then it passes this information to the next neuron. So that is something called fully connected neural network. And we see this as input, that's the output, and somewhere in between we call them hidden layers. In this case, there's only one hidden layer, and you can have many. And in our mathematical terms, it's a neuron with all these weights. So we know what a neuron is, and we know how they are connected together to form this neural network. There's still one important piece that's missing. How does each of these neurons know what kind of W values it should have. Without those W values, it wouldn't work properly, and we have hundreds and thousands and millions of those neurons. How does the neuron find out its own W values? Well, that is through a process called gradient descent. Here, I simplify the network. I put one neuron here, assuming there's only one neuron, and the input, I assume there are only two inputs. Let's assume the input is an image of either dog or cat. And I assume the image is so small that it has only 2 pixels, has only 2 inputs. A 2-pixel picture comes in. The 2 pixels comes in, so you do this. Remember that we have the weighted sum with this W1, W2. It does the activation. And then, let's say we feed in a cat image. You go through the network, and the network thinks it's a dog. It comes out with 0.9, which thinks it's very likely a dog. And that's wrong. If it's wrong, that's an error, right? That's a delta. And mathematically, we call that loss function, but for understanding purpose, it doesn't matter. We just call that an error. So now we got the error. What we want to do is go back and tweak this W1 and W2 a little bit so that the error is smaller. And want to keep tweaking this W1 and W2 until, in the very end, the error ideally should be 0. That's what we wanted to do. That's the concept of gradient descent. As what you can see here, this is W1. We can have many values for W1 and many values for W2. And the z-axis is the error. When you put in different values of W1 and W2, you get different errors. What we want to find is this lowest point where the error is the minimum, closer to 0. So initially, W1, W2 might be somewhere here. Some random value, somewhere. And how do you get down to 0? Well, imagine right now you're being dropped in a dark night in a mountain, in the middle of the mountain. And you cannot see far away, only a few meters right in front of you. So how do you get down to the mountain? One way to do it is to stand where you are. You go 360 degrees, you look down and see which direction brings you the maximum decline, and then you do one step forward. And then with the new position, you go around and see which direction goes down the most. You do another step, and so on and so forth. At the end, you will get down to the bottom of the hill. And that's how gradient descent works. So, as illustrated here, you start from here, you look around, you say, well, this number goes down the quickest. So it goes down here. And then, with this number, you look around all its neighbors. You're saying, well, this number, these two numbers are the same. I'm going to pick one. So you come here. Again, after coming, it comes here. You go around and say, I'm going to come here because it goes down the quickest. And then at the end, you are down to the hill. So that's a basic concept, and that's how all the neural network today, or deep learning neural network today, are being trained. In mathematical terms, we're using derivatives to do this. For my purpose, I'm not going to go into details. Maybe later, we are going to into a bit more details when Joe, you will talk about this. For now, you just need to know that we have some mathematical tools available to do what I just described. With all this knowledge equipped, we put them together. This is a neural network. First, this is how training works. You feed in some information, some known information. Let's say it's a dot image. You calculate the result. Moving forward, you get the result. You compare the result with the actual result. Well, the model thinks it's a cat, but it's actually a dog. There's an error, So you go back and tweak the parameters, those W values of each of these neurons one by one. You go all the way back. You tweak them all a little bit. And then you give it another image. Again, with the new image, the network does its calculations, generate a new result. With that new result, you get another error. With the error, you come back with the gradient descent concept. You tweak each of these parameters a little bit, all the way back. Back and forth, back and forth. That's how you tweak all these parameters. In the end, you will predict. So now you already know the basic concept of a neural network. It's not that hard. Next, I hope my network works. If it works, I'm going to give you a demo. So, this is a basic neural network. We have two inputs, right? And you see this gray thing are those parameters. So, first of all, we have some inputs, 1 and 0, that comes in. And we go forward, you calculate this, the weighted sum of this, and weighted sum of this guy, weighted sum of this guy. So that's the first layer. And then all these three is going into this neuron. So we run it. And then this guy is calculated. So now you can see that there's a value here, a 0.4545. That's what it calculates. The actual result from this particular example is expecting a 1. So there's an error. With this error, we are going to go back. We remember the backward. It comes back, took these parameters a little bit, and then you go back, took the parameter of this guy a little bit, and so on and so forth. After it took all the parameters, it feed in a new number. Oops. A new number, and so on and so forth. Reach the last node. It comes back to all these parameters, so on and so forth. If we do a full run, you can see all these numbers are jumping, and at the end, you get to 0.62 something. And my machine seemed to be controlled by somebody for some reason. So you can see here, well, it's not 1, exactly 1. That's because this network is not complex enough. If we build a more complex network, it will reach 1. And next, I'm going to show you something more fun. Okay, so let's pick this guy here. As you can see here, there are some dots, some orange, some blue. The task of this network is try to predict which dot is which, to separate them into classes. And you will assume if I give this, after it's trained, if give it some new dots, let's say if a new dot is something close to here, you would think it's blue. If it's somewhere here, you would think that's something orange. All right, so with this particular network, let's train it. As you can see here, very quickly, the model starts to learn this part should be orange, this part should be blue. Now, if we try again, we'll reduce these neurons, right? Right now we have 4 neurons. Let's say I reduce it down to 2, see what happens. Well, it comes up with a different result. It's trying to think, all dots in here is orange, all dots in here is blue. So as what you can see here, with different types of neurons and different architecture, it's coming up with different result. Let's try something more fun. Like this one, it's more complex. Even for a human being, right? If I give you a new dot, let's say here, Do you think it should be orange or blue? So with this neural network, if it's a 2x2 network, let's see what it does. It's thinking pretty hard. While it's training, you can actually see this line. That's the error that we just talked about. You can see this error is going down when you try to train. It's trying to figure out something, not quite. It's trying to say this part has to be blue, this has to be orange, but what about these dots? It didn't quite figure out. So let's make a more complex network here. Let's say we give you a lot of neurons here. We give you another layers. These layers we want to give you, let's say 4. I'll give you another layer. Oops, sorry. So I'll give you another layer. And this one also comes 4. And let's see what it does. This is a much more complex neural network here. Let's wait a while. As you can see here, these lines, this thing starts to come up first, and then it's dropping down. It's trying to learn. As you can see here, it's trying to create this weird shape. And if you look at each of these neurons, each neuron is doing different things. For example, this particular neuron is trying to be sensitive to the upper portion and the lower portion. And this particular one is doing another thing. Each neuron is doing its own work. At the end of the day, you can see it's coming closer and closer. And at the end, if you wait enough time, it's going to do this classification pretty well. We've seen how neural network works. Simple concept, right? Weighted sum, a division, put them up all together. With gradient descent, we can train it. We just show how it's being trained. With that basic knowledge in mind, we're going to computer vision, which is in deep neural network, that is a field where we have the most recent development. Computer vision is something that's hard for machine, but for human being, it's just intuitive. Even for a 3-year-old, they can do something quite amazing.
Okay, that's a cat sitting in a bed. The boy is petting the elephant. Those are people that are going on an airplane. That's a big airplane.
Well, that's how a 3-year-old can recognize all these objects in the picture and translate them into language. Today, we're not going to talk about the language part. That will be, I don't think we will have time to go through that. Let's focus on the computer vision part. How does a 3-year-old recognize all these things? And how does computer learn to do the same thing? By the way, this video is from a TED Talk by Fei Li, who is a professor in Stanford University. Right now, she's taking a 2-year break working for Google. So it's in TED Talk. It turns out that human being, your retinal cells have different types. Each of them are sensitive to different things. For example, some retinal cells are sensitive to red color. Some are sensitive to light intensity. Some are sensitive both to movement, so on and so forth. Each of them are responsible for different things. It gathers its own information, and then you pass the information to the next region to process for the process. In order to simulate that, we invented something called kernel or filters. And let's see what it is. Well, as you can see here, that's a human face, a picture. This is a black and white picture, so we get all the numbers. It's represented by the numbers. If it's color, it has 3 channels RGB. Same idea. So each of these pixels is represented by a number. And then we have a 3x3 matrix. Again, also numbers. What's amazing is that if apply those numbers to the picture, for example, this particular filter, we show the numbers here, it does the job of sharpening. As what you can see here, the original image on the left, and compare that with the image on the right, you can see all this edge of the face is sharpened. And you can see the eyes. What happens here is that we use this matrix, scroll through this image one by one. For each one of those pixels, we're doing this matrix multiplications, a element-wise multiplication and sum them up together. And we do it across the whole image, we come up with this new image. And if we, let's see whether we can have, it'd be hard for me to see here. Get the last one. Okay, so here's a building. If we choose a kernel, let's say it's bottom level, you can see here, it picks up all these horizontal lines that's at the bottom of an object. Or if we do this left, again, this time it picks up all these vertical lines on the left of something. So it's amazing that these kernels, as easy as these 3x3 numbers, can do this amazing job. But this is not something new. When you play around with Photoshop, that's how it works. Sharpen an image, for example. Now, this thing is called kernel. It's sensitive to different things. That's similar to human retina cells. It's sensitive to different things. With that in mind, that's how convolutional network works. We have these kernels. It scrolls through this picture and generate a new image called feature map. And as you can see here, that's a zoom-in version of how it works. You have this filter, you do this simple multiplications and addition, it comes with a new number, and you scroll through it, you generate all these numbers, it creates the feature map. That's how convolutional neural network works, right? You have a kernel, you scroll through the image, you create this feature map. But one filter is not enough. As what I mentioned, some kernels should be, it's sensible to, let's say, horizontal lines. Some are sensible to some curves. Some are sensible to some vertical lines. So we have different filters. Each of them create a separate feature map. Now, we put them up together, we have something very similar to human being. We have an image that comes in. We have the retina cells. We process the image that comes to this region, V1 region, right? And then with this processed information, we have another region that abstracts from V1. Let's say in V1, we recognize all this basic shape like curves and lines. At V2, we might recognize the shape of an eye or eyeball. And then from then on, to the next region with this eye shape and eyeball, you recognize the whole eye and nose. And then the next region, you combine all this together, you recognize a human face. So it's layer after layer after layer. And that's how it looks like in the convolutional network. You have input image. You have a lot of filters. You create a lot of feature maps. And that's the V1 in the last slide. And then with that, you have some new filters. You abstract through this feature map, you create another feature map, and so on and so forth. At the end, you see different objects. And that's another way to look at it. Again, you have different kernels. Each kernel generates different feature map. So you have many, many layers. At the end, you recognize the object. It's from the very basic thing of like pixels, to lines, to colors, all the way down. Right? And again, all these filters have those 3x3 parameters that you need to take. Same idea here. You do a forward pass. You try to predict whether it's a dog or cat. If it's not correct, a backward propagation will tweak the parameter inside these kernels a little bit, and then you give a new image. Go the forward pass. You predict again. There's an error. With the gradient descent theory that I just presented, you go back, tweak all these kernels again. At the end, all these kernels are learned automatically. We have never told each kernel which one should be responsible for red color, which one should be vertical lines. It just learned. We have never told them to do that. Those great guys created a tool to let us explore into these kernels and neurons to see how it works. And luckily, my machine is not cooperating. I cannot do the real demo here, but I can show you a video. Okay, so as you can see here, all that you see here, each one of those little squares correspond to a filter. And what's shown here is what are those filters sensible to. For example, this guy is very sensible to red color. And this guy is very sensible to that kind of lines. So they're all sensible to different things. And if you move on, okay, so now you can see this particular neuron. Nothing else is activated, but this guy is activated because you have a sharp contrast, white and black. Now, pay attention to the neuron next to it. Okay, now when the paper passes to the right, you can see the next neuron gets activated, meaning that it's also sensitive to sharp contrast, but the other way around, it's black to white. So that proves that each different neuron is sensible to different things. And you get all these different layers, we just mentioned, many layers. And each layer has many neurons, and each neuron, you can see they're doing different things. Now, if we go to some layers up here, it's pretty abstract right now. You can know some abstract concept like face. You can see this process moving. You can see this neuron, the green guy here, is sensitive to faces. And you can see that's what it captured. And as what you can see here, to prove that it's only sensitive to faces, as you can see here, this person stands up. In here, we don't see anything below the shoulder, meaning that this neuron cares only about faces. It has the concept about face, even the person moves around. And well, if you give you a cat face, you recognize it too. And next, we give you a book. Surprisingly, this neuron gets activated. Well, during this training, we never tell the neuron to recognize text, but it does anyway. And the reason is that when we train this, well, this is a neuron trained to tell different things. And one of the things is bookshelf. It has to recognize this as a bookshelf. In order to know this as a bookshelf, it has to know there are books on the bookshelf. How does it know it's a book? Well, there's some text on it. That's how you learn about text. So after the network is trained, you see it's sensitive to this text, different text. So let's go back. Okay, so with all these computer vision stuffs, amazingly, here's what a machine can do now. Similar to a 3-year-old.
A large airplane sitting on top of an airport runway.
Not too bad. That's what the AI does, with the simple things that we just introduced. In the past 2 or 3 years, we have achieved a lot in computer vision. Actually, a lot of them has surpassed human capabilities. For example, in the ImageNet computation, which is a computation with 1,000 different real-life objects, like different dogs and cats, different ships, different vehicles. In 2015, they did a test. Human being has 5.1% incorrect rate, but machine has passed that. It's only 4.94. That's another example. CT scan. As you know, CT scan is 3D. This is a top-down view of a slice. So for the doctor to know whether you have cancer, you actually get this slice, it moves down. You see these little white dots. Because cancer, when it's in the initial stage, is really, really small. You do the slice, you slice down, you can see this white dot comes in, and then it goes out. That's how you notice that it might be a cancer cell. So again, machine does a better job. The machine missed 0 cases versus some experts who were in the field for 20 years, they missed 7% of them. And driverless cars and trucks. We heard in the news a lot. In 2016, Uber did the first delivery with a driverless car. And that's something happened this year. Baidu, which is the Google equivalent in China, they did the competition for face recognition. And they picked these twins, and they picked these really old photos, and told the human being, who are also experts, and the machine to compete. And machine won by a small margin. So in all these cases, we can show that AI, computer vision today, has achieved to such a point that in a lot of fields, it surpasses human being. Wow, but it also made mistakes. Look at this. But if you look at it, think about it, it's not too wrong, right? It's just lacking a sense of history and arts. And what about this? Well, if the computer have never seen a baseball bat, it doesn't know it. Well, there's still a long way to go, right? That's where the opportunity lies. With all that said, let's move on to the next thing, which is also related to computer vision, AlphaGo. We just introduced Dr. Lee here. He's an expert in this area. So later, we're going to maybe invite Dr. Lee to talk something in more detail about it. I learned about reinforcement learning from Dr. Lee. So for those of you, maybe you don't know too much about Go, why is it so hard? The goal is with this 19 by 19 matrix, the grids, and you simply put the black and white stones on the board. Now, the combination of all these things is what makes it so hard. Let's put it in perspective. In the whole universe, there are 10 to the power of 80 atoms. In the whole universe, not in the world, in the whole universe. So how many combinations of this Go valid move do you think it has? Anybody want to take a guess? That is the number. It's a lot bigger than all the atoms in the universe. That's why it's so hard to solve. That's why it makes such a big deal. Like AlphaGo came along and beat the top players in the world. So let's think of it. If the combination is huge, there's no way for a computer to iterate through all the possibilities, which is the strongest point of a computer. It's fast. How does it achieve the goal? It turns out that computer vision, that's what we just introduced, play a major role in here. What happens is that this goal layout is just, you can look at it as a 19 by 19 grid of picture, right? It's a graph. If we get a lot of this place, feed it into a computer vision network and tell it to predict. It turns out that that's how human beings are trained. A human being know how to play Go because when they were very young, they are told to play a lot of these existing game scripts. That's from the 1,000, maybe 2,000 years ago, all this famous game script, they are recorded. Human beings will memorize thousands of those scripts. And each game has hundreds of moves. So human beings store all these layouts in their brain. When they see a new layout, they don't need to look at all these 19 by 19, 361 positions in order to know where to move next. They have the intuition. They look at the layout, you quickly match to something that they played before, even though they are not exactly the same. Once they match the past layout, they will say, wow, with this layout, all that I need to care is about maybe, let's say, bottom right. Those 4 or 5 moves are valid. Everything else, I don't need to consider. That's how human beings play. So for computers, we do the same thing. We get thousands and thousands of this real human play layout, feed it into this computer vision network. That's what we just introduced, convolutional network. And then the end result is to predict what is the next move human is going to play. Apparently, in the beginning, you will generate an error. So go back to all these parameters and feed in another move. It do another prediction. There's an error. Go back to the parameters, so on and so forth. That's what we have introduced. And at the end of the day, it knows how to predict human move pretty accurately. That's how computers start to have intuition. Give it a layout. It can now zoom in from this big board into this little area. When you can zoom into the little area, like 5, 6 grids, now computer has an advantage because for computer to search, to brute force all those 5, 6 grids, well, human cannot compete with computer speed. So AlphaGo trained the network. That's the network that we just mentioned, policy network. Give it layout, it knows what is the next move. Intuition. In a split second, it knows where to move next, around the area. And then they also train something called value network. So give it a layout. For human being, a good player, you give it any layout, in a second they will tell why it's going to win, or black is going to win. They don't need to calculate. Give it layout, they look at it for a second, they will tell you who is going to win. Same for this value network. So we feed in this layout as a picture, image, to the network. And the network is to predict who's going to win. Again, we do all this training, and then computer has this intuition. It knows who's going to win with what probability. We combine these two together. Now, this is another topic on its own, reinforcement learning. I won't go into details, but reinforcement learning is how human beings learn. Remember what we have been talking, computer vision and things. We are talking about supervised learning, meaning that we give it some facts. It's a dog, it's a cat, it's known. That's supervised. It's like classroom kind of learning. The teacher tells you what's correct, what's wrong. Reinforcement learning is another type of learning. Like human being, how do we learn without teacher? We try, we fail, and then we learn. That's how reinforcement learning works. So let's say a human being gives you a new video game. You have never played before. What do? You try different things, right? You might pick up this thing, oh, it got bursted, so you will try avoid it next time. And if you pick up this thing, well, you get some bonus. You remember that. You try to pick up that next time. Put that into AlphaGo, because we just have this policy network and value network, we know what to move next. So in the news, we heard of that AlphaGo plays with itself, right? What does it mean? That's exactly the trying process. So you have the left hand and right hand. They both have this intuition. So the left hand would say, I want to move to this position. And it has its right hand say, if you move to that position, I'm going to here, so on and so forth. At the end, so for each move, the valuation framework will know who's likely to win. And then at the end, after the left hand and right hand play all the way to the end, one of them will win. That's an experience, either good or bad. With that either good or bad experience, you go all the way back and update all these moves. Say, each move is a good or bad. And then next time, you tend to do these good moves and you avoid the bad moves. That's reinforcement in a nutshell. Today, there are a lot of topics we are not going to cover. This is one of these latest development in last month. As what you can see here, computer vision can now transfer this horse into a zebra in real time. For the computer to do that, it has to know, separate the horse from the background and foreground, and also to transfer the style. And that's called the GAN, Generative Adversarial Networks. And later on, our IBM folks will show you something similar, artistic things. But I'm not going to talk about how it works, because we're late today, we'll skip this part. Another thing we wouldn't talk about is NLP, Natural Language Processing. Well, something got me into this was when I first looked at this thing. Well, computer can figure out. That would mean the NLP model really understands the meaning of words, which is amazing. So that's a topic on its own we can find another time to talk about. Again, this is something called computer memory. We feed in some text. It's like a book. Well, those are simple text. It's like when you teach your 5-year-old. With all this text, you give it to the machine, and then you start to ask questions. Very surprisingly, the machine can answer 95% of the questions right. So machine can understand the text and memorize them. All right, so now we have some understandings of how deep learning neural network work. It's not that hard. The question is, why do you want to learn it here and now? Let's talk about the why here first. Actually, Canada is one of the countries that heavily invested into AI in the world very early on in the 1980s. Deep neural network was invented in the beginning of 80s or maybe end of 70s, and then it got hot for a while. But then, as I mentioned, because of the limitation of computing power and such, it didn't fly. So it becomes a very cold area. Nobody cares about it. But Canada actually came with this research foundation and invested heavily into it, and it attracted one of these guys whose name is Geoffrey Hinton. He's named the godfather of deep learning because he invented the backpropagation and the gradient descent, all those theories we just talked about, and it just worked. Geoffrey Hinton was in UK, and then his research funding was cut, then he moved to US, and then in US his research funding was also cut. And luckily, Canada has this thing, so he came to U of T and stayed there. And that's why Canada becomes the hub of deep learning at that time. And we have also some other big guys. If you are into deep learning, you will have to hear those names. That's why Toronto is actually the place about deep learning. And then the second question is, why now? I don't know how many of you heard of the news. In March, we announced the federal budget. The federal will invest $125 million into this thing called Vector Institute, plus $25 billion from private institutes like Google, Facebook, also a lot of Canadian players, such as RBC, TELUS, TD Bank, have Loblaws. This Vector Institute is responsible for research in deep learning, and this is right here in Toronto. And the biggest thing is that Geoffrey Hinton, who was hired by Google, is now coming back to Toronto. With his reputation and profile, he's going to attract a lot of talent here. So that's a golden opportunity for us, all the folks here in Toronto. So back in March 31st, Geoffrey Hinton was here giving a talk in UFT. And I had a chance to ask Dr. Hinton a few questions. One of them being, well, the neural network I just introduced here is something so basic, right? A little bit of neurons, put them into layers, doing this back and forth, and then it works. Human being, the brain must be a lot more complex. So I asked him the question that, what do you think is the next move from this basic neural network? And the answer, well, he's doing a lot of research on something called capsule, which simulates the brain regions, how it works. But he said that it's not ready for public release yet. He has been working on it for quite a few years. But I believe when that's released by Geoffrey Hinton, so I believe there will be a fundamental change in the whole world about deep learning. That all being said, right, if by any chance now you are interested in deep learning, I hope you are convinced that it's not something really hard. Even though today we have all the PhDs here, I don't get a PhD. That's why in the very beginning, it's really hard for me. There's so many different things I need to choose. I don't know where to start. I spent a year trying different things. I went nowhere. In the end, I found all that you need to do is to leverage your own strength. For myself, I've been developing software for my whole career path. So for me, it's easier for me to read the code rather than the paper. So that's what I did. And it's actually pretty easy in today's world because there are so many tools. An example being, I'll quickly show you. We all heard about driverless car. And this is something called Deep Tesla. As you can see here, there's a piece of code here. All that it does is to define the neural network that we just mentioned. 10, 20 lines of code. And as you can see here, for each of these neural network, it's showing you what's being activated. And you can also go to this visualization. That's the actual image that's being fed into the network. The blue wheel shows how human being is driving. And the white is showing how your own network is predicting. That shows all this and shows the training progress. And while you train for a longer time, you will see this thing goes down, which means the error narrows down. So that's a tool that you can use. So when I first started, I borrowed a code from Jeremy Howard, who is the former president of Kaggle and chief scientist. I borrowed his library and wrote this 7 lines of code. Amazingly, it can recognize dogs and cats at 97% accuracy. And not only that, One of my friends likes fishing. So I tweak this code a bit. I tell it to recognize all different types of fish, and it works. So this works not only for dogs and cats. For 200 types of fish, it does the job. What I'm trying to say is that you don't necessarily need to have a lot of knowledge. Once I get into this, I now learn the entire process of like what does validation means, what does this loss function means, and then I go deeper and deeper. Right? It's something that you just need to get yourself started and focus on your strength. So moving forward, we're thinking about a few things that we can potentially do, and I would like to hear from all you guys. So I originally planned for a survey, but looks like the network is not working well. So I would like all you guys to follow us so that we have some discussion online. You can see 3 WeChat code here. Don't scan them all, scan just one of them. The reason why I put up all the 3 here is because each one has only 100% capacity. If you see it full, scan another one, but don't scan them all. We will have some discussions later on to see what you guys like. And that will conclude my presentation. Thank you.